In the previous video, we classified all groups of orders 1 through 3 up to isomorphism. In this video, we're going to continue by talking about groups of orders 4 through 8. Now, with groups of orders 1 through 3, the story ended up not being too exciting. There was only one group of each possible order, and they were all just cyclic groups. Well, with groups of orders 4 through 8, I think you'll see that things are a little bit more interesting. Let's start with groups of order 4. If G is a group of order 4, then it turns out that G is isomorphic to one of two different groups. It's either isomorphic to the cyclic group of order 4, and we covered cyclic groups extensively in the previous video, or it's isomorphic to another group called the Klein 4 group. I'm going to give you several different explanations for how to construct the Klein 4 group, but first of all, let me explain to you what it is by just showing you its multiplication table. The Klein 4 group is a group of order 4 with an identity element and three other elements which I've labeled as A, B, and C. Now, from the multiplication table, there are a few things that you can tell right away. First of all, because the multiplication table is symmetric across the main diagonal, it means that the Klein 4 group is an abelian group. That's something that we also talked about in the previous video. A group is abelian if and only if its multiplication table is symmetric across the main diagonal. Now, the second thing that I want to point out here, which you can also see from the multiplication table, is that A times B is equal to C. That's something which is worth remembering when I show you the other descriptions of this group. Finally, you might have noticed that the main diagonal consists entirely of identity elements. And if you think about what that means, it means that A squared, B squared, and C squared are all equal to the identity element. That implies in particular that none of the elements of this group are generators for the group. So the group is not isomorphic to the cyclic group of order 4. So the takeaway message here is that up to isomorphism, there are exactly two distinct groups of order 4, the cyclic group of order 4 and the Klein 4 group. Now, at this point, I'm not going to try to prove that these are the only two groups of order 4 up to isomorphism, but for now, you can just take as a fact that there are exactly two groups of order 4 up to isomorphism. Now, there are a couple of other ways of describing the Klein 4 group, and I'd like to talk about those right now. The first is using what are called generators and relations. This notation is somewhat similar to the notation that we used when we introduced cyclic groups, except there we only had one generator, and we didn't list any relations. Now, the truth is that when you describe a group using generators and relations, it can be a little tricky to get it right, but what it indicates is that, first of all, every element of the group can be written as a finite product of the generators and their inverses. In such a finite product, you're allowed to use generators more than one time. So for example, you could have A times B inverse times A times B inverse, or any other finite product of A's and B's and their inverses. Now, the reason why I put and their inverses in parentheses here is because in a finite group, you don't need to worry about taking negative powers of the generators. You can just stick with non-negative powers, and they will already generate the whole group. But in general, in infinite groups, the rule is that every element of the group has to be a finite product of the generators and their inverses. Now, the relations are just equations involving the generators and the identity element of the group. And the second thing that this notation indicates is that the generators satisfy all of those equations, and that any other relation satisfied by the elements of the group can be deduced just from these relations. Now, in practice, when you're trying to write a group using generators and relations, that's usually the really tricky part to check. And that's one of the reasons why describing a group using generators and relations is really not, in general, an easy task. But the flip side of the coin is that once you're given a description of a group using generators and relations, which, by the way, is called a presentation for the group, it does then make it a lot easier to work with elements of the group and to deduce basic facts about the group by using the relations. Now, one thing you may be wondering is where the element C went in this description of the Klein 4 group. Well, of course, C turned out to be equal to AB, so it's something that we can write as a finite product of the A's and B's. And also, it's pretty easy to see that any relation satisfied by the element C could be deduced just from the listed relations satisfied by A and B. So for example, in our previous description of this group, using the multiplication table, we said that C squared was the identity. And since C was AB, that's the same as saying that AB squared was the identity. Now that doesn't appear as one of the relations in our list here, but we can deduce it pretty easily from these relations. First of all, AB squared is AB times AB, and then by generalized associativity, that's A times BA times B, Then, using the fact that AB is BA, we can write that as A times AB times B. And again, by generalized associativity, that's A squared times B squared. And finally, by our relations that A squared and B squared are both the identity, that's just the identity times the identity, which is the identity. So the relation that C squared is the identity, in our previous description of this group, is built into this description using generators and relations. Similarly, any other relation that you could find between the elements of this group can be deduced just from these relations that are listed here. Another way of describing the Klein 4 group is using what are called direct products. This is a very important construction, so you should try to make sure to understand it 100%. If you have two groups G and H, with binary operations star and circle, then their direct product is the group consisting of the Cartesian product of G with H, together with a new binary operation, which I'm just writing as a dot here, defined in the following way. For any two elements of the Cartesian product of G with H, G1H1 and G2H2, G1H1 dot G2H2 is defined to be the new element of the Cartesian product whose first entry is G1 star G2 and whose second entry is H1 circle H2. In other words, the group elements in each of the individual components of the Cartesian product interact with each other using whatever binary operation is defined on that group. Now, of course, the notation for the direct product of two groups G and H is just G cross H. And as I mentioned in one of my previous videos, you just have to be a little careful to discern when someone is talking about the Cartesian product of two sets versus when someone is talking about the direct product of two groups. Usually that's pretty clear from context, but there are some cases where it's worth clarifying. Now, I guess that technically we should check that the direct product of two groups is actually a group. And while this is a good exercise to make sure that you understand the definition, it's also not too difficult, so I'm going to go through it quickly. I'm also going to suppress all the notation for the binary operations involved. That way I don't have to write a lot of stars and circles everywhere. So the first thing that we need to check is that the binary operation that we define on the Cartesian product of G with H is associative. And that means we need to think about what happens when we multiply together three elements of the Cartesian product. Well, if we do this multiplication by multiplying the first two first, and then multiplying the result with the third, it's going to give us something that looks like G1 G2 times G3, comma H1 H2 times H3. Now, the key to verifying all the properties that you need to check to show that G cross H is a group is to use the corresponding properties in the individual groups G and H. So by associativity in G and in H, I can move the parentheses over in each of the components here, and then I can trace backwards through the analogous steps to show that this element of the Cartesian product is what I would get by multiplying the three original elements together with the parentheses on the right. Therefore, the binary operation that we define on the Cartesian product of G with H is an associative operation. How about existence of an identity element? Well, there's an obvious choice for the identity element, and that is the element of the Cartesian product whose first component is the identity element in the group G, and whose second component is the identity element in the group H. As long as you understand the definition of the binary operation that we define on G cross H, it should be pretty easy for you to see that for any element GH in G cross H, if I multiply GH by that identity element, either on the left or on the right, then since each of these is an identity element in its corresponding group, I'm just going to get back GH. That verifies the existence of an identity element. And finally, how about existence of inverses? Well, at this point you've probably caught on and figured out that the inverse of the element GH is just going to be the element of the Cartesian product whose first component is the inverse of G in G and whose second component is the inverse of H in H. It's very easy to verify that when you multiply that element by GH, either on the left or on the right, then using the definition of our binary operation on the Cartesian product together with the fact that these are inverses of G and H in their respective groups, you just get back the element that we call the identity element of the Cartesian product. That verifies the existence of inverses in G cross H, and it shows that the direct product really is a group. Now let's think about what happens when we form the direct product of two cyclic groups of order 2. Let's let G be a cyclic group of order 2 generated by an element X, and let's label its elements as E sub G for the identity and X. And let's let H be a cyclic group of order 2 with a generator Y, and with elements E sub H and Y. Then, as a set, the direct product of the two groups G and H is just the Cartesian product, which is the set of all ordered pairs of elements of G, comma, elements of H. To understand the group structure of the direct product, let's label these elements. We'll call the first one E because we know it's the identity in the direct product, and we'll call the other elements A, B, and C. Now, if I build the multiplication table of this direct product, it looks like this. Because, for example, if I multiply A by itself, then I get x squared comma the identity, and since x squared is the identity in G, I end up with the identity in G cross H. So A squared is the identity. And similarly, if I multiply A times B, then I get an x in the first coordinate and a y in the second coordinate. So I end up with C. And so on for the other elements. But the thing that you should check about this multiplication table is that it's the exact same multiplication table as the one for the Klein 4 group. And so our conclusion here is that the Klein 4 group is actually isomorphic to the direct product of two cyclic groups of order 2. So this is yet another way of defining this group. Now, because direct products are of fundamental importance in group theory, I want to go ahead at this point and also define the direct product of a finite collection of groups. And the definition is not that much different. Let's suppose that I have n different groups G1 to Gn, each one possibly with its own binary operation. Well then, I can define the direct product G1 cross ... cross Gn to be the Cartesian product of these sets, together with the binary operation defined by the rule that little g1 ... little gn times little g1 prime ... little gn prime is little g1 g1 prime, little g2 g2 prime ... little gn gn prime. Now, I've suppressed all of the binary operations here, but the two most important things to be careful of are that number one, in each of the components here, I'm combining the two elements using the binary operation in the corresponding group. And number two, order in general does matter. So if you write G1 to Gn first and then G1 prime to Gn prime, then the element on the right-hand side should say G1 G1 prime ... Gn Gn prime. And you can't reverse the orders of any of these multiplications in general, because the groups G1 to Gn may not be abelian groups. Next, let's talk about groups of order 5. Here the story is pretty simple again. If G is a group of order 5, then it turns out that G has to be isomorphic to the cyclic group of order 5. Now, I'm not going to prove that this is the only group of order 5 up to isomorphism, but it is a general fact that we'll prove later that anytime P is a prime number, there's only one group of order P up to isomorphism, and that's the cyclic group of order P. It's very easy to understand why this is true, for example, as a consequence of a theorem called Lagrange's theorem that we'll prove in a later video. Now, with groups of order 6, the situation is a little more interesting again. It turns out that there are two different groups of order 6 up to isomorphism. There's the cyclic group of order 6, C6, and there's another group called D6. And now, if you think about this, I'm sure that you're going to have some obvious questions. The first of which is, what is D6? Well, D6 is the dihedral group of order 6, and we're going to talk about it in detail in just a few minutes, so just wait for that one. The second question, which you may or may not have thought of, is why is the direct product of C2 and C3 not on the list above? C2 is a group of order 2, and C3 is a group of order 3, so the direct product of C2 and C3 is a group of order 6, but somehow it didn't make it into the list. Well, the reason why, which I will explain in just a minute, is that C2 cross 3 turns out to be isomorphic to C6. And maybe that's a little surprising to some people, but it's not difficult to see why that's true. Okay, the third question which some people might have is why isn't S3 on the list above? Now, if you don't know what S3 is, then you probably wouldn't have thought of this question. S3 is the symmetric group of degree 3, and we're going to talk a lot about symmetric groups in later videos. But in case anybody is wondering about this now, S3 is another group of order 6, but it turns out that it's isomorphic to D6. So up to isomorphism, there are actually only two groups of order 6. Every group of order 6 is either isomorphic to the cyclic group of order 6 or to the dihedral group of order 6. Now, before we move on to talk about dihedral groups, I'd like to zoom in on this claim that C2 cross 3 is isomorphic to C6, just to make sure that you believe me. So first of all, let's choose generators x and y for C2 and C3, so that the elements of the Cartesian product are just the 6 ordered pairs that you see here. Now what I'd like to show you is that this element xy by itself generates the entire group, so that it's actually a cyclic group. To see that, just start taking powers of xy. Of course, xy to the 1 is just xy. And by the definition of the binary operation in the direct product, xy squared is just xy times xy, which is x squared y squared, and since x squared is the identity in the cyclic group of order 2, that's just the identity comma y squared. By the way, I forgot to mention, I'm labeling the identity in the cyclic group of order 2 as E2, and the identity in the cyclic group of order 3 as E3. Okay, well, what about xy cubed? Well, to figure out what xy cubed is, I can just take xy squared and I can multiply it by xy. When I do that, the first components multiply, giving me an x, and the second components multiply, giving me a y cubed. And since y cubed is the identity in the cyclic group of order 3, this is just the element x comma E3. Now, it's not difficult to convince yourself that when you take an element of a direct product to a power, you're really just going to take all of the components to that power. And so using that fact, you can compute that xy to the fourth is x to the fourth y to the fourth, which is E2y, and that xy to the fifth is x to the fifth y to the fifth, which is xy squared. Finally, xy to the sixth is x to the sixth y to the sixth, which is just the identity in the direct product. And now the thing to pay attention to is that these 6 powers of the element xy have now traced out all of the elements of the group. That means that the direct product of C2 and C3 is a cyclic group generated by the single element xy. But as mentioned in the previous video, there's only one cyclic group of any given finite order, and so this has to be isomorphic to the cyclic group of order 6. Next, let's talk about dihedral groups. For n bigger than or equal to 3, the dihedral group of order 2n, D2n, is the collection of all rigid motions preserving a regular n-gon centered at the origin in the plane, with the binary operation being composition of maps. Now, there's a few things here that I need to explain, and the first is, what do I mean by rigid motions? Well, when we talk about rigid motions of the plane or rigid motions of Euclidean space in general, we just mean isometries, and isometries are maps from the space to itself, which preserve distances between points. To make this even less mysterious, it turns out that using linear algebra, it's pretty easy to classify the collection of all rigid motions of Euclidean space, and they turn out to just be translations, rotations, reflections, and compositions of these. Now, since D2n is the collection of all rigid motions preserving a regular n-gon centered at the origin, and no non-zero translations are going to preserve the origin, the rigid motions that we need to consider in this definition are just rotations and reflections and compositions of rotations and reflections. So this is kind of like the rotation groups that we talked about in the previous video, but the main difference is that now we're allowing reflections. Now, I'm going to give you some examples with pictures, but first of all, I just want to make sure that we believe that this D2n is actually a group. So the first thing that we should check here is associativity. But as I mentioned in the previous video when we were talking about rotation groups, composition of maps from a set to itself, in this case from R2 to itself, is always an associative binary operation, so associativity does hold. Now the identity map on R2, which just sends every point to itself, is clearly a rigid motion of R2, and it serves as the identity in this group, because if we compose this function with any other function from R2 to R2, we're just going to get the other function back. Finally, to check that every element of this group has an inverse, if you look at the collection of rigid motions that we listed from R2 to R2, they're all bijections, so they all have well-defined inverse functions. It's also not difficult to convince yourself that the inverse function of a rigid motion is another rigid motion, so it's another element of the set of rigid motions. And of course, it has the property that when you compose it with the original function either from the left or from the right, you get the identity map back. So that establishes the existence of inverses, and it shows that D2n is in fact a group. Now let's look at a few examples, and let's start with the simplest example when n is 3. Here we're considering the collection of rigid motions of an equilateral triangle in the plane centered at the origin. And of course, all of the rotations which preserve the equilateral triangle are going to be in this set. So we have the identity map, the rotation counterclockwise by 2 pi over r radians, which I've labeled as r, and then the rotation counterclockwise by 4 pi over 3 radians, which is r squared. Now remember, because we're using multiplicative notation and we're suppressing the binary operation, r squared really means r composed with r. So it means that you do r once and then you do it again. Another thing which I'll remind you about, which can be confusing to some people, is that when you're trying to understand what compositions of maps do to the points in the space that they're acting on, you should always work from the inside out or from the right to the left. Here it doesn't really make a difference because it reads the same from right to left as from left to right. But in some of the other calculations that we're going to do, the order that we read the maps in is going to make a difference. Okay, so are these all the rigid rotations of an equilateral triangle centered at the origin? Well, of course, we haven't considered reflections yet, and it's pretty clear that if we reflect about a line passing through, say, the green vertex and the origin, we obtain another rigid motion of this triangle which is not in our list. Note here that reflection is an orientation reversing transformation, so it changes the order of the vertices when you read them in the counterclockwise direction. Well, now that I've discovered this new transformation, I can also think about what happens when I compose it with R. To figure out what SR or S composed with R is, I work from the right to the left. So first I apply R, which rotates the original triangle counterclockwise 2 pi over 3 radians, and then I apply S, which reflects this triangle through the vertical line passing through the origin. That gives me the triangle pictured here, and that's a new rigid motion that's not in our list. Similarly, if I compose S with R squared, so I first apply R squared and then S, I end up with another rigid motion. And now it's not difficult to convince yourself that these are all the possibilities. To see why that's true, any rigid motion of the triangle has to take the green vertex to another vertex of the triangle. That's number one. And then number two, because it's a rigid motion, it has to take the yellow vertex to a vertex which is adjacent to the green vertex. Now, there's 3 possibilities for where the green vertex goes, and once you've decided where to send the green vertex, you have 2 choices for where to send the yellow vertex. If you send the yellow vertex to the nearest vertex clockwise from the green vertex, then you're going to obtain one of the orientation-preserving rigid motions on the left here. On the other hand, if you choose to send the yellow vertex to the vertex which is nearest counterclockwise from the green vertex, then you're going to obtain one of the orientation-reversing rigid motions on the right-hand side. Those are all the possibilities, so they give us all the elements of the dihedral group of order 6. Now I'd like to take a closer look at this and mention a few facts about the dihedral group. First of all, it's pretty easy to see that R cubed is E, and that S squared is E. And another way to state those 2 facts is to say that R inverse is R squared, and S inverse is S. Another important relation between R and S is that RS is SR squared, and since R squared is R inverse, that's the same as SR inverse. This relation is not too difficult to see, so first, let's think about what the map RS does to our triangle. In order to understand that, working from the right to the left, first we apply the map S, which is our reflection about a vertical line passing through the origin. And then we apply the map R, which is our rotation counterclockwise by 2 pi over 3 radians, and we obtain the triangle pictured here. On the other hand, if we apply the map R squared first, then we rotate our original triangle counterclockwise by 4 pi over 3 radians, and if we then apply S, we obtain the same triangle. But this sequence of maps corresponds to SR squared, so that shows that RS is equal to SR squared. Now, it turns out that these 3 relations can be used to derive every other possible relation between the elements R and S of this group. And since every element of this group is a finite product of R's and S's, that means that we have a presentation for the group. It's the group generated by R and S, subject to the conditions that R cubed and S squared are both the identity, and RS is SR inverse. At this point, you don't even need to remember what R and S are, because any group given by generators and relations like this is going to have to be isomorphic to D6. So this is another way of describing the dihedral group of order 6, without any reference to rigid motions. Now finally, in case you haven't noticed this yet, RS was SR squared, and SR squared is not the same thing as SR. That means that this is a non-abelian group. And since all of the other groups of orders up to 5 were abelian, this is the smallest non-abelian group. So now things are starting to get a little more interesting. Well, now that we're getting good at this, let's look at another example when n is 4. So here we're considering the collection of all rigid motions which preserve a square centered at the origin in the plane. Of course, there's the identity map, and there's also the rotation counterclockwise by pi over 2 radians. Well, if we just compose that map with itself, and then do so again, we obtain all the possible rotations which preserve the square. Now, learning from our example with the triangle, we could also consider what happens when we reflect the square about a line passing through one of the vertices and the origin. In this case, I'm going to pick the line with slope -1 passing through the origin, just because of the way that I've oriented the square in my picture. Well, that fixes 2 of the vertices, and it switches the order of the other 2, thereby reversing the orientation of the vertices on the square. Now that I have this reflection, I can also think about what happens when I compose it with the rotations. that gives me 3 new elements of the group. And then, by the same argument that I talked about last time, where we considered first where the green vertex maps through, and then one of the adjoining vertices, we can argue that this is all the possible rigid motions which preserve a square centered at the origin in the plane. That means that these rigid motions are the elements of the dihedral group of order 8. Similar to what we talked about with the triangle, the rotation r here has the property that r to the 4th power is the identity, and the reflection s has the property that s squared is the identity. It's also not difficult to see in this case that rs turns out to be equal to sr inverse, so that if we apply s to our original square and then r, we'll end up with the same map as if we apply r inverse and then s. Now it turns out that these relations again are all the ones that you need to know in order to derive any other relation between r and s. So this is a presentation for the dihedral group of order 8. And it's very similar to the presentation for D6, except here it's r to the 4th instead of r cubed equals e. In general, for n bigger than or equal to 3, the story is very similar. The dihedral group of order 2n is generated by a rotation by 2 pi over n radians, together with a reflection about a line through the origin and some fixed angle. The order of this group is 2n, which justifies calling it the dihedral group of order 2n, and it turns out to always have a presentation analogous to the ones that we saw in the cases when n was 3 or 4. It's generated by r and s, and every relation between these two generators can be obtained from the relations r to the n equals s squared equals e, and rs equals sr inverse. Now just like we saw when n was 3, the fact that rs is sr inverse, and the fact that r inverse is r to the n minus 1, and that sr and sr to the n minus 1 are different elements of the group, means that this group is always a non-abelian group. So now we have an infinite collection of non-abelian groups, one for every even number 6 and greater. Okay, now let's move on to talk about groups of order 7, and let's see if you can guess what groups of order 7 look like. Well, if you were paying attention before, then you should know that up to isomorphism there's only one group of order 7, which is the cyclic group of order 7. And that's because 7 is a prime number. So it follows from the general fact that I mentioned when we were talking about groups of order 5. That's kind of the end of the story for groups of order 7. So let's move on to talking about groups of order 8. Well, here the story is pretty interesting, because it turns out that there are 5 different non-isomorphic groups of order 8. If you'd like to try to guess what they are, you can pause the video and guess now. This is one of my favorite test questions when I'm teaching abstract algebra, and it's something that I think that everyone coming out of a first course in this subject should know. So first of all, there's the cyclic group of order 8, and I hope you got that one, because there's a cyclic group of order n for every positive integer n. Secondly, there's the direct product of the cyclic group of order 2 and the cyclic group of order 4. Now, I hope this is not confusing to anybody, because when we were talking about groups of order 6, we said that C6 was isomorphic to C2 cross C3. But here we're saying that these two groups are non-isomorphic. Well, they really are not isomorphic. If you take a look at C2 cross C4, you're not going to be able to find a generator for the group, and so it's not a cyclic group. The reason for the difference in behavior here has to do with the fact that 6 equals 2 times 3, and 2 and 3 are relatively prime, but 8 equals 2 times 4, and 2 and 4 are not relatively prime. Anyway, I wouldn't worry too much about that now, but you can just believe me that these two groups are not isomorphic. Now, if you believe me that these two groups are not isomorphic, then you should also believe me that C4 is not isomorphic to C2 cross C2, and that gives us another way to build a group of order 8, which is to take the direct product of C2 with C2 with C2. That gives us a group of order 2 times 2 times 2, which is 8, and it's the third non-isomorphic group in our list. Okay, so what about the other two groups? Well, there's another one here that I hope that you got, because we just looked at it, and it's the dihedral group of order 8. And the final group on the list is one that you probably only got if you've seen it before. It's what's called the Quaternion group, and it's the last group that I want to talk about in this video. Now, before we move on, it's worth pointing out that the first 3 groups in this list are all abelian groups, but the last 2 groups here are both non-abelian groups. And so here, all of a sudden, you have 5 different non-isomorphic groups of the same order, which shows you that for some orders, things can get a little bit more complicated. In order to describe the Quaternion group of order 8, let me label its elements as 1 minus 1, I minus I, j minus j, and k minus k. 1 here is going to be the identity element, and I'm treating this as a multiplicative group. Now, rather than write out the full multiplication table for this group, I'll just explain some key relations from which all of the other products follow. First of all, because 1 is the identity, 1x and x1 are equal to x for every x in the quaternions. And secondly, for every x in the quaternions, we define negative 1x and x times negative 1 to be negative x, with the convention that negative negative 1 means 1, negative negative I means I, and so on. Next, I, j, and k all have the property that when you square them, you get negative 1. And finally, to understand what happens when you multiply i's, j's, and k's together, you can take a look at this little diagram that I've drawn. If you multiply I and j together, you get k. If you multiply j and k together, you get I. And if you multiply k and I together, you get j. But if you reverse the orders of the multiplications, then you flip the sign. So j times I is negative k, I times k is negative j, and k times j is negative I. That gives you the 6 formulas written here, and these rules are enough to determine the rest of the multiplication table. So for example, if you want to know what negative I squared is, then you just write that as negative I times negative I, which is I times negative 1 times negative 1 times I, and then you move the parentheses to the middle, use the fact that negative 1 squared is 1, and then use the fact that I squared is negative 1. Similarly, negative j squared and negative k squared both turn out to be negative 1. In any case, one of the important things to realize here is that because ij is not the same as ji, and similarly for some of the other products, this is a non-abelian group of order 8. Finally, I'd like to finish this video by briefly reviewing all of the groups of orders up to 8 up to isomorphism. First of all, for groups of orders 1, 2, and 3, there are only the cyclic groups of those orders, and no other groups up to isomorphism. But for groups of order 4, there's the cyclic group of order 4 and the Klein 4 group. Now, one of the things that we showed that you might want to remember is that the Klein 4 group is isomorphic to C2 cross C2. Next, there's only one group of order 5, which is the cyclic group of order 5. But for order 6, there's the cyclic group of order 6 together with the dihedral group, which I've written in yellow in order to indicate that it's not an abelian group. The dihedral group of order 6 is the smallest non-abelian group on our list. Now here you should remember what we mentioned, that the cyclic group of order 6 is isomorphic to C2 cross C3, and that the dihedral group of order 6 is isomorphic to the symmetric group of degree 3, which we'll talk about in a later video. Moving on, there's only one group of order 7 up to isomorphism, which is the cyclic group of order 7, but there are 5 different non-isomorphic possibilities for groups of order 8, which are the ones that we've listed here. This is all of the groups of order 8 up to isomorphism, and it gives you some things to compare with as we move forward and talk about different examples in coming videos. That's the end of this video. Thank you for watching. In the next video, we're going to move forward and, with a view toward talking about the integers modulo n and quotient groups, we're going to talk about equivalence relations.